In this lesson, I'm going to introduce you to a new functional group called alkenes. We've seen alkenes before, and they're not actually that new to us, and they're also not that different. So this is kind of a baby step up from alkanes to alkenes. Alkenes are characterized by the carbon-carbon double bond. A carbon-carbon double bond right here involves two sp2 hybridized carbons, and the nomenclature for alkenes is very similar to the nomenclature of an alkane. If this didn't have the double bond, then I would just call this compound heptane. When it's an alkene, you just change the ane to an ene, and now you have your new name for this compound right here. Now, the problem with this compound and its name is that currently this name does not tell me where the double bond is occurring. And the double bond will always be numbered according to the carbon where it starts. And so if I start calling this the number 1 carbon, then I would encounter that alkene at the 1, 2, 3, 4, 5 position. If I call this the number 1 carbon, then I would call it 2-heptene. And you probably correctly guessed that you want to number your parent chain so that you encounter the alkene as quickly as possible. So the name of this compound right here is 2-heptene. That name is incorrect, and we're going to fix the problem with it in just a second. But I'm going to move on to the next compound first, and then I'll go back and address what's missing in this name. If you're wondering and you can't move on with your life until you find out, it's an issue of whether or not the alkene is cis or trans. And we have a different way of saying that with alkenes. But that's kind of the issue here, is that this is actually a trans alkene, and I'm going to have to deal with that in the nomenclature later. So I can start also naming the next two compounds. They both also have 7 carbons in the longest continuous chunk of carbons. 1, 2, 3, 4, 5, 6, 7. So this is also going to be some type of heptene. That alkene is going to come off of one of the carbons, and I'm going to just leave a number symbol in there for now, and I'll fill that in a second. You'll notice there's also a chloro group coming off of this and a methyl group. So I'm not bothering to number the parent chain yet, and I'm just going to leave here that there needs to be some number. I'm going to come back and fill that in a second, but this just kind of allows us to see what all 3 of these compounds have in common before we go back and address what they don't have in common. This third compound over here on the far right, that is also some type of heptene. The alkene on that heptene is coming off of some position, but this is actually a heptenol, where we have both an alkene and an alcohol occurring on our 7-carbon parent chain. And when you have these types of enols, they're called, you have to number the parent chain alcohol in the middle of the word. So in spite of the fact that this kind of makes it difficult to say the name smoothly, it's going to be some number heptene dash some number all. And we'll deal with what those some numbers are in a second. I also have 2 methyl groups coming off of here, so this is a dimethyl. And those methyl groups are also coming off of the parent chain at some numbers. That 3 was inadvertent and not a slip of what I'm going to number these things in a second. Okay, so what I've done now is I've come up with 3 names for these compounds. None of the names are currently correct, but all of the names have the basic kind of structure, the skeleton of what your correct name needs to look like. Let's fill in the numbers first. Now, alkenes have priority, meaning that we care when we're numbering the parent chain that we get to an alkene quickly. And this now gives you a list of 3 different types of things that you're going to encounter in terms of their priorities. So let's make a little note here that in Chem 351, that's the course you're currently taking, alcohols are the highest priority. When we start expanding our rules of nomenclature priority to include things like aldehydes and ketones and carboxylic acids in the 2nd semester of this series, then alcohols are no longer going to be the highest priority. But for this class, alcohols will always be the highest priority. Alkenes are 2nd highest priority. Alkynes which we'll get to later on in the semester, are third highest priority, and alkyl groups slash halides are the lowest priority. And this is essentially all of the priority rules of nomenclature that you're ever going to need to worry about in all of the semesters that you attempt to take Chem 351. That sounded pretty dark. In the only time that you'll need to take Chem 351 because you're definitely going to pass the class. All right, so we didn't have to worry about priority competitions because in this first compound, there was only one thing on it. In the second compound, I have a chloro group, a methyl group, and an alkene. Well, a methyl group is an alkyl group. It's the lowest priority. The chloro is a halogen. It's also the lowest priority. So the alkene is the highest priority, and that means that I choose the numbering system that gives the alkene the lowest number it possibly can. And so I'm either going to number from the right side or from the left side, and if I number from the right side, then my alkene will show up at the 2 position, and that forces my methyl to be at the 4 position and my chloro group to be at the 5 position. So now I've added in the correct numbers to this name. The name is still incorrect because I haven't specified what this double bond is doing in my name, but we'll come back to that in a second. Now for the third compound, the alcohol is the highest priority. So the purpose of me using this example was specifically to force you to choose between giving the alcohol the number 2 position or giving the alkene the number 2 position. And based on these priority rules that we have right here, the alcohol gets the number 2 position. So I'm going to call the alcohol number 2. That means that my methyl groups are occurring at the 3 and the 4 position, and my alkene is starting at the 5 position. Now, let's address the problem that I've been carefully avoiding, and this has to do with the cis versus trans nature of a double bond. The terms cis and trans are crude approximations, meaning that the only time you can actually get away with using the terms cis and trans is when you have a double bond, and I'm going to think about the double bond in 2 halves, this pi bond right here. Actually, I'm thinking about both the sigma and the pi, so the double bond is the better term to describe this. On this double bond, if you draw a line perpendicular to the double bond, then you have divided it up into the 2 halves that I care about. On the right-hand side of my double bond, there is a hydrogen and an alkyl group. On the left-hand side of my double bond, there is also a hydrogen and an alkyl group. The terms cis and trans can only be used when both sides have one and only one hydrogen on it. So another example of a compound that fits that criteria would be 2-butene. And this is actually a very common compound to use simply because it is the simplest possible example. We can use cis and trans to describe 2-butene because on either side, when we draw a perpendicular line to my double bond, on either side there is one and only one hydrogen. So we have a hydrogen here and a hydrogen here. And a correct name for this compound right here would be trans 2-butene. The trans is a stereochemical designation, and it is not used for alphabetization purposes. In fact, it's hardly used at all. We use something else, but for now we can use trans, and this trans only works when you have a double bond and there is one and only one hydrogen on both sides of that double bond. If now I put a second hydrogen on this side right over here, oops, the hydrogen didn't go where I wanted it to. If I put a hydrogen right here, this is no longer a cis or trans compound, and the reason for that is that this doesn't matter. There's no difference between the top or the bottom side of my double bond. So let's go back to that trans and make sure you understand why I called it trans. If you remember ring nomenclature, hopefully that idea makes sense to you, that trans refers to the idea that these things have changed. That as I went from one side of the plane of my double bond, so let's get rid of that line and now think about this line. This line is now within the plane of the double bond. On the left-hand side, above the plane, there is a methyl group And on the right-hand side, below the plane, there is a methyl group. So this is the trans configuration. If, whoops, well, probably didn't need to do it this way. I could have just relabeled them, but oh well. Now, this right here is a totally different molecule, and it is called cis-2-butene. So let's go back to those two. We'll compare them side by side. This compound on the left-hand side is cis-2-butene, and this compound on the right-hand side is trans-2-butene. These two compounds right here are not mirror images of each other. If we get rid of the hydrogens, you can kind of see that if you held cis-2-butene, the one on the left-hand side, up to a mirror, you would see cis-2-butene. So cis and trans are not mirror images of each other. The definition of enantiomers is that they are non-superimposable mirror images of each other. Since these alkenes are not mirror images of each other, then they are stereoisomers that are not enantiomers. And if something is not an enantiomer, the only other option that we commonly see is diastereomers. So these two compounds are diastereomers of each other. And that's true for any type of cis-trans pairing, is that they are going to be diastereomers of each other. All right. But the compound that I'm looking at didn't actually ask you about the compounds we've been, the 2-butene. Instead, we've been looking at this compound right here. And because both sides of this have hydrogens on it, then we can absolutely refer to this as a trans-2-heptene, and that is a correct name. So this is a correct name for this compound, trans-2-heptene. Control. There we go. Trans-2-heptene. That is a correct name. It is not the best name. And the reason for this, and we'll see this with later examples, is trans and cis can only be used when we have this rule, that I'll say it one more time, that you can only use cis and trans when both sides, when we draw the line perpendicular to it and think about right side and left side, when both sides have one and exactly one hydrogen, then we can get away with the trans and the cis. Well, what if it's not a hydrogen over here, but what if it's a chlorine? And hopefully you can appreciate that this molecule right here is different. Let me change this. I'm going to put the chlorine on the other side. These two are not the same compound. They are not superimposable on each other. They are stereoisomers of each other. Specifically, what type of stereoisomer? Well, if it's a difference of being on one side or the other of the double bond, then they are diastereomers of each other. Or if you remember our functional definition of an enantiomer is that we flip all the chiral centers. Well, a chiral center is an sp3 hybridized carbon. This compound has no chiral centers. And so the difference between these two compounds is not me flipping all the chiral centers. And by our working definition, where enantiomers are when you flip all chiral centers, then these are not enantiomers of each other. And the only other option is diastereomer. So these are diastereomers of each other. And I need to come up with a term to describe them. Whoops. I had extra hydrogen. Now they are diastereomers of each other. You might have been wondering what was going on there. I forgot to erase that hydrogen. So the difference between these two compounds is that methyl versus a chloro group right there. So this is why we need something that allows us to compare these two compounds. And instead of trans and cis, we use the concepts of E and Z. So I'm going to go back to this original compound right here. And now we're looking at really the more meaningful examples, the simple examples of this is E2-heptene, and E is equivalent to trans. So E is equivalent to trans, and Z is equivalent to cis. I believe that these words are German, and E stands for something in German, like entgegen. My German pronunciation is not in my skill set. And Z is zusammen, which means same, and E would mean opposite. So that's kind of where we use the terms cis and trans, where you can think about trans as opposite sides or changed, and cis is same sides. Okay, when they started using the terms trans and cis to describe gender, I was very confused as an organic chemist. It took me a while to figure that out. I had to go look some stuff up. All right. So for an organic chemist, trans and cis refer to orientation across the plane or a double bond, but only when you have two hydrogens on both sides. And now we're going to use the terms E and Z. So a correct name for this compound right here would be E2-heptene, and this over here would be Z2 E2-heptene. And that's typically the nomenclature that the ChemDraw will give you. They call it Z2-heptene, and this one over here they're going to call E2-heptene. And you can put the number right here in between the T and the E, and that's okay. It's just difficult to say, and I prefer to put the 2 out in front. So this is how ChemDraw chooses to name this comp. So let's go back to the problem. Okay, so now we have E2-heptene, and I'm going to put that name out here in front. It is technically italicized and not a euro. There we go. And if that wasn't the symbol for a euro, then clearly I need to set up a GoFundMe page to go to Europe to find that out. That's the only place I could know that for sure. All right, now for this compound right here, there are 2 hydrogens. So there is a hydrogen poking up on this side and a hydrogen poking down on this side. So we could absolutely use the cis and the trans labels. This would be trans 5-chloro-4-methyl-2-heptene. So it is correct because it follows that very limited rule that you have to have one and only one hydrogen on both sides. It is absolutely correct to use the trans label on this one, but it is more common instead to use the E label. That's the more common label, and it's a little bit more modern. It makes more sense as we get into more complicated examples. This one right here, that double bond, also has a hydrogen going up and a hydrogen going down. So from the hydrogen's perspective, things have changed. It's switched on either side, so this would be E as well. And if you happen to have installed ChemDraw on your computer, this is a useful way for you to kind of practice these. You just kind of draw some hypothetical compounds and then try to name them and see if ChemDraw agrees with your name. All right, let's add a layer of complexity, though, and let's come back to this compound right here first. I'll zoom in a tad. So let's first let ChemDraw tell me what the name of this compound is. So Control-Alt-N. There we go. And again, ChemDraw likes to put that 2 in a weird place, but hopefully that matches the name I came up with. No. Oh, curses. I definitely had the name wrong. I did not count correctly. That's embarrassing. 1, 2, 3, 4, 5 is the methyl, and 6 is the chloro. So yeah, I had this wrong. Thank you, ChemDraw. 1, 2, 3, 4. Yeah, I think I did the other one correct, but we're going to find out in a second. Some of you probably were watching the video wondering why I didn't count that carbon in the middle. That's because I screwed up. That's why I didn't count that. Okay, so now we have the name of this one corrected. Let's go ahead and pretend that we know what the chirality of that methyl group is. And what you'll notice with this right here is that I didn't change the compound, so the name stayed the same, but I did add a chiral center into that compound. And we lump those chiral centers together in parentheses out in front of the compound. And the R designation right here, I specify that it's the 5 position. And let's go ahead and do the same thing over here with that chlorine. And that's really why they've specified the number. Because there are 2 different chiral centers in this compound, then you need to specify which chiral center is the 5 position and which one is the 6 position. And maybe not the best example. This is a little better. And that's why you need to put numbers on there. If you just call this R, S, E, then your audience would not know which one was R and which one was S. It would, though, know which one was E because you only have one double bond in the system. And if you were to put a second double bond in this compound, so this is not the question that I asked, but let's pretend that this was. Now, because there are 2 different double bonds and both of them happen to be E, then you definitely want to label those. So if I were asking this question on an exam, and I had given you this compound right here, then I would actually accept this E right here with a number, and I would accept that E without a number. And I would also accept the E at the end of the list or the E at the beginning of the list because it's technically 2E. And you want to put these in numerical order. So there's quite a bit. I would accept a variety of things. What I would prefer would be this: 2E, 5R, 6S. There, now I have all of my stereocenters are clearly labeled. I know which stereocenter I'm talking about at which position. And I've also put them in the numerical order. This in my opinion, is the best name for this compound right here. So that's the one I'm going to put. So again, what I did is I took all of my stereocenters. I named, so sorry, stereocenter refers to something that's either chiral or an easy double bond. And so I have all three chiral centers right here clearly identified. I've got them in numeric order, and this is probably the best way of naming this compound. Okay, so let's go ahead and update my name now. So, and it's different because I did change the question a little bit. I added in those two chiral centers, so this is 5R6S. Those are not italicized. Not that anyone cares besides me. There we go. I'm still a little rattled by the fact that I counted incorrectly. So let's move on. Last compound right here. You'll actually notice that there are 1, 2, 3 potential chiral centers. And so we can go ahead and add those into our name. And I'm going to go ahead and just randomly assign these as coming towards you, which means there's a hydrogen going away. And we'll have this one going away from me and this one going away from me. And so now let's practice naming this with all of the chiral centers. This carbon right there is chiral. The oxygen is the highest priority group. And then there is a hydrogen that is the lowest priority group, and it is poking away from me. So this is already set up correctly. And so it's going to go, the oxygen is the highest priority, and then this carbon right here is the second highest priority because it is connected to 2 other carbons. And then this carbon right here is the third highest priority because it's connected to 3 hydrogens. So that means that this is rotating in an R fashion, and the hydrogen's going away from me, so that means I'm looking at it correctly. So I'm going to go ahead and put the R label on there. The next one. For this chiral center, I have 3 carbons. Carbon here, carbon here, carbon here. The carbon on the bottom is a carbon connected to 3 hydrogens. That's a methyl group. The carbon on the right-hand side is a carbon connected to 2 other carbons and a hydrogen. And this carbon over here on the left-hand side is a carbon connected to an oxygen and a carbon and a hydrogen. So hopefully this rings some bells in terms of remembering how to designate stereocenters. So when I think about this carbon as a chiral center, then the highest priority thing connected to it is this carbon right here because it's connected to an oxygen. The second highest priority would be this carbon over here because it's connected to a carbon. And the third highest priority would be this carbon down here because it's only connected to 3 hydrogens. So I should be able to put a stereochemical label on there, and it's S. And why would that be? Well, the answer is that I'm looking at this thing backwards. The lowest priority substituent is a hydrogen that's poking towards me, and therefore I'm looking at it in reverse. And so this looks to me like it's R, but because I'm looking at it backwards, it's actually S. Let's see, I'm going to keep those labels for the next one. All right, now the last chiral center. This chiral center right here, there are 3 carbons, 1, 2, and 3. The carbon above is the simplest one, so that's just the carbon connected to 3 hydrogens. This carbon over here is a carbon that is connected to 2 carbons and a hydrogen. And this carbon on the right-hand side is connected to a carbon and a hydrogen that's coming down, but it's actually connected to that carbon twice. So it gets the same designation. I'll put that right there. All right, so we have a problem, and that's that it's tied, that this carbon over here is tied with that carbon based on the Kahn-Ingold-Prelog rules. So that means I need to move out to the next highest priority. So that means I look at this carbon right here. So I'll steal this one, and that carbon right there is attached to another carbon on the right-hand side. It has a pi bond going back to the stereocenter, and it has a hydrogen. So that means that this carbon over here is connected to a carbon-carbon hydrogen. And if we go out a layer, this carbon right here is connected to an oxygen, a carbon, and a hydrogen. So I'll put that label right here. This carbon right here is connected to an oxygen, a carbon, and a hydrogen. So now I'm ready to establish the priority. So this is, of the 4 things coming off, the hydrogen is the lowest priority. And it's actually coming towards me, so whatever label I come up with, I've got to switch it. Okay? Then, of the remaining ones, then this carbon over here on the left-hand side is higher priority than the carbon on the right-hand side, because the carbon on the left-hand side is connected to a carbon that's connected to an oxygen, and the carbon on the right-hand side is connected to a carbon that's only connected to another carbon. So the arrows are going to look like this. It's going to go from this carbon to this one to this one. That looks an awful lot like it's going in an S fashion, but because this carbon in the center right here is, because the hydrogen is coming towards me, that means I'm looking at it backwards, so it should show R. And we'll get rid of all of this mess. And now we're ready to name the compound. And so for this compound, there are 4 different labels on our heptenol. And then we have these 2 methyl groups, dimethyl. So I'm just going to reproduce. And the alkene is coming off of the 1, 2, 3, 4, 5 position. The alcohol is coming off of the 2 position. The methyl groups are coming off of the 3 and the 4 positions. I'm going to double check my numbering. So this was the number 1 carbon because it's the side closest to the oxygen. That means this carbon is number 2, and that's where my alcohol is. Number 3 and number 4 are my methyl groups. Number 5 is my alkene. 6 is the end of the alkene, and 7 is just a plain old carbon. All right, the alkene is showing up at the 5 position. So it is a 5E. And then at the 2 position, I have an R. At the 3 position, I have an S. And at the 4 position, I have an R. Notice how I like to see these in numeric order. So even though there's R's and S's here, I like to put them in numeric order. ChemDraw doesn't really care. It usually puts all the RS labels first and then the EZ labels second, unless there's multiple EZ labels, and then it's... Anyway, ChemDraw gets weird. So just put a number on everything and then put them in numerical order, and your answer will be good enough. Let's see if ChemDraw agrees with me. All right, so 3,4-dimethyl hept5-enol. So sorry, whatever that says. We are in agreement on this side, and then I have a 2R, 3S, 4R, and then I called it 5E, and they just kind of put the E at the end. So again, I prefer to see these in numeric order with a number on each one of your stereocenter when you have lots of stereocenters like in this compound. Okay, so we're going to add in the name. So this is 2R3S 4R5E. And I need to italicize all of the letters, because if not, it's going to bug me. And I'll do that while you're not looking. Okay, so that was kind of a tour of nomenclature for these compounds. Let's continue that tour. The next question asks us, or tour if you prefer, the next question asks us to name the compounds, and then we're going to talk about which one is most polar. So, to the ChemDraw. So our first compound right here is a 3-carbon group. So this is definitely going to be some type of propene. The alkene is going to occur at the 1 position if I number it from this side, or if I start on this end, it will end at the 2 position. And we definitely want the 1 position. So this would be 1-propene. And there's also a fluoro group coming off the 1 position as well. So I always spell that wrong. Fluoropropene. Ones are optional, so you could be lazy and just call this fluoropropene, and your audience would figure out that everything was happening at the 1 position. But we can't be so lazy as to not identify it as cis or trans. And remember that when something contains a hydrogen on either side, which has been all the examples you've seen before, then you can assign you can either use cis or trans, or you can use the better E and Z designations. And I'm definitely going to use the E and the Z designations. And since both hydrogens are on the same side, then it is Z. My professor one time referred to it as the ZAME side, which was cringy but definitely helpful when I was taking exams. So this is Z-fluoropropene. And ChemDraw is going to be a little bit more creative by giving you all the numbers and giving them to you in places that make it difficult to say it out loud. But this is a simpler name, and this will work. So let's go back now and name this one. Well, we don't probably need ChemDraw to help us with this one, but we'll use it anyway. This is another 1-fluoro-1-propene, and the alkene is now trans. So this is going to be your E, fluoropropene. And the last one right here is no longer everything happening at the 1 position. So this alkene 1, 2, 3, that's a propene. The alkene is the 1 position because it has higher priority. So it's definitely going to occupy the 1 position. And the fluorine is going to occur at the 2 position. So this compound right here is now 2-fluoropropene. And we don't have to specify if the double bond is E or Z. And the reason for that is when you think about a horizontal line that cuts through your double bond, the only time you have to worry about E and Z designations is when both sides of your double bond, left and right, are different on the top versus the bottom. So the right-hand side is different. There's a methyl group on top and a fluorine on the bottom, but the left-hand side is the same. There's 2 hydrogens. That means that no matter how anyone in the world draws 2-fluoropropene, as long as they put the alkene at the 1 position and the fluoro at the 2 position, there's no way to draw it wrong. And the fluorine and the methyl group are going to be Z to a hydrogen and E to a hydrogen, both of them. So in order for us to worry about E and Z, then we have to see differences on both sides of your double bond. We only have differences on one side of the double bond here, so there's no E or Z designation on this compound. If you're still not convinced by this, think about it this way. I could take these 2 hydrogens and flip their sides, and I still have exactly the same compound. So E and Z is to help you know which side you have to draw things on, but since it doesn't matter, since both of them are the same, then we don't bother with the E and the Z designation for this third compound. So I've done the first part now. I've named the following molecules. So good for me. The second part is to still be bothered by my lack of counting practice, but now to move on past that and think about polarity. So let's go back to ChemDraw again. These bonds are polar. The bonds are polar. So not necessarily the whole molecule. We'll talk about its polarity in a second, but the bonds are polar. And I'm going to use this arrow right here to describe how electron density is moving. On this bond right here, because the fluorine is so highly electronegative, then the electrons are moving off of this carbon and onto that fluorine. Carbon is more electronegative than hydrogen, so that means that the electron density is moving off of the hydrogen and onto the carbon. Although this arrow right here really isn't that important, and the reason is yeah, electrons are moving from the hydrogen to the carbon, but the hydrogen has so very little electron density that it's just not even worth dealing with. If there's other atoms in the molecule, then you really don't care what hydrogen's doing because it doesn't have enough electron density to significantly donate electron density in one direction down a bond. If you wanted to draw it proportionally, it would look something like this, and that would be your little arrow right there. That's kind of what that hydrogen is doing. It just has so little electron density to give that we're just going to ignore it. And what we really care about is the relationship between this carbon and this fluorine. We also care about the relationship between this alkyl group and this carbon right here. And what we find is this carbon right here. I'm just going to call this an R group and be as generic as possible. So it doesn't matter if it's a methyl or an ethyl or whatever it is. If it's an alkyl group, then this is just a regular R group, and this carbon up here is sp3 hybridized. And the carbon down here is sp2 hybridized. And if you remember from the very beginning of the semester, during the Alex Nightmare portion of the course, you would have been forced to regurgitate that S, in terms of electronegativity, sp is more electronegative than sp2, which is more electronegative than sp3. And so this means that the sp2 hybridized carbon in an alkene will actually pull some electron density down from this alkyl group. And if we draw that to scale, it's not nearly as impressive as the beating that the fluorine is giving to that carbon. Whoops, that's not letting me do that very well. But it's more substantial than what the hydrogen was trying to do. Okay? That got ugly quickly. So we'll just draw a little arrow right here. Okay? So there is some electron density that moves down this carbon right there from the alkyl group to the alkene group, and then some electron density that's being moved from this carbon to the fluorine. And now what effect do the pi electrons have? Well, pi electrons are like water in a bathtub, and these electrons are very polarizable. They are sloshy. They will move back and forth across this pi bond in whatever direction the bathtub is leaning. And so what happens here is when the fluorine pulls electron density away from the carbon, it creates a hole that the pi electrons fill. And so you actually see the electrons on the pi bond shift over to fill that hole, and then this bond is also helping. So these two different groups, the R group and the fluorine, are pushing the pi bonds in unison, working together, moving the electron density over onto that fluorine. So that actually makes this particular molecule fairly polar. And what would it look like if we had a different molecule? Well, that's kind of the point of the question. So let's go ahead and get rid of these hydrogens because I pointed out that they're kind of pointless. They don't do anything in this. But now let's look at the E fluoropropene. And so I got the fluorine over here, and I have the R group up here. So this is my E fluoropropene if this is a methyl group. We're going to be generic and just refer to any old R group right here. And now let's think about what these arrows are doing. Okay? The fluorine is still winning the tug of war for electron density, and this R group is dumping some electron density down, which means that this right here, the pi bond, is definitely sloshing over to this side of the bathtub. And so both of these compounds are fairly polar, and they're not polar enough to dissolve in water because they don't make good hydrogen bonds with the water. But they're fairly polar. If we were to measure it, we'd be surprised at how polar the fluorine tends to make this hydrocarbon. But which one is more polar? That's what the question is asking. And so what we want to do is one more time think about the axes. So on the pi bond there is you can think about a line that is perpendicular to the pi bond and a line that is parallel to the pi bond. And so I'm going to think about what's going on along the parallel line to the pi bond and what's going on the perpendicular line to the pi bond. What you'll notice is that these two groups, the R group and the fluorine, are working together along both axes. In other words, both of them are pushing more or less to the right. Okay? So along this parallel axis, they are working together. And both of them are working together along the vertical axis. They're both pushing down. So there is complete agreement about what these two groups are doing relative to these two axes right here. Whereas in this compound, they are both working together along the horizontal axis because they're both more or less pushing to the right, but along the vertical axis there is some disagreement. This one is pushing down and this one is pushing up, so there's some disagreement there. Of those two axes, the parallel one is much more important. You really can't slosh water in a bathtub up and down as well, because I know some of you probably will now go try that. You can slosh water up and down, and good for you, and get a mop, but it actually doesn't work as well. When you slosh water across this pi bond, just like water in a bathtub, the side to side is much more important. So the fact that these two are working together along that side to side sloshing of the pi bond is much more consequential than the fact that they're working against each other. So these are both relatively the same polarity. This one has a slight edge because along the vertical axis it does have some cooperation that this one is missing. So when I'm ranking these in terms of polarity, let's clean these compounds up now. And we'll go back to the original compounds that I was talking about. When I'm ranking them in terms of polarity, my Z fluoropropene is going to be slightly less polar than my E fluoropropene, because in the E fluoropropene, they are working together in every axis. And in the Z fluoropropene, they are working together along the most important axis, but there is some disagreement along the vertical axis. And so now let's think about the last compound. This one. We had a methyl group over here, and we had a fluorine right here. And this was that 2-fluoropropene. The bond angles aren't quite ideal. That feels better. And what you'll notice is that this fluorine is pulling electron density this way, and the R group is giving a little bit of electron density down this bond right here. And so now we think about the two axes, the horizontal axis and the vertical axis. And they are collectively, along the vertical axis, there is good agreement. They are pushing electron density up. So that's good. Along the horizontal axis, they are not in agreement. The R group is pushing it this way, more or less to the right, and the fluorine is pushing it more or less to the left, and they are in disagreement along that horizontal axis. So, relative to the other two compounds, we expect the E-fluoropropene to be the most polar, because you have agreement on the horizontal and vertical axes, because they're plural. And rather than think about this as horizontal, it's actually better to think about it as parallel to the pi bond and perpendicular to the pi bond. We'll call this perp. All right, so there's agreement along the parallel and the perpendicular axes. In this compound right here, it is agreement on the perpendicular axis, and there is disagreement on the parallel axis. For the other compound over here, they disagreed on the perpendicular axis, so one was pushing up and one was pushing down, but they had agreement along the parallel axis. So this is 2 for 2. This is great. It's the most polar. That's obvious. These ones are 1 for 2, and so now we're going to split hairs, and the hairs are not that small. When there's agreement along the parallel axis, that is much more important than agreement along the perpendicular axis. So then this compound would be the least polar. And if you know that this one is the most polar and this one is the least polar, then I'm hoping you can figure out that this one is in the middle. So, let's see. Did ChemDraw... Oh, let's see what's going to happen when I close this. Oh, yeah. Now it made a mess. Oh, well. We're going to leave that alone. All right. I cleaned everything up and wrote out what I think the best answers are. E-fluoropropene, this one in the middle, is the most polar, because the electron density is being moved with agreement by both the methyl group and the fluorine on all axes. I would refer to this on all axes. Z-fluoropropene is the second most polar, this one over here on the left-hand side, because the electron density is being moved with agreement along the axis parallel to the pi bond. That is the most important axis. And since the axis vertical to the pi bond is not as important, I didn't even bother to put that in the answer. 2-fluoropropene is the least polar because the electron density movement is offset, meaning that the fluorine and the methyl group are in disagreement when they're trying to move this along the axis parallel to the pi bond. Okay. All right, now that you have some feel for the physical properties and the nomenclature of alkenes, let's move on to their chemical properties, and this has to do with the heat of combustion. Remember, heat of combustion is the energy that's released when you set these things on fire. And if you look at this heat of combustion table, there's a bunch of these negative 3,000 values. Typically, we report these values as positive values, and sometimes in the figurehead, they'll actually say the negative heat of combustion. And what that allows them to do is come along and just report all of these as positive values like this. So watch out for that. Sometimes they'll actually just put absolute value of heat of combustion, which looks like this, if you remember absolute value ideas. And that's probably the most useful way to think about this, is we want to know what is the total quantity of energy associated with burning these. That's what absolute value asks. So in any event, I'm just going to leave this here as a negative value so that your general chemistry instructor is not upset that I'm ignoring the fact that heat of combustion gives off a negative value because it's releasing heat. Just organic chemists, we get tired of that negative symbol because when you burn something, you're always going to give off heat. So why focus on the negative? We move on to the positive. All right, so first question is, why is 1-octene so much higher than everyone else in terms of heat of combustion? And that is probably a painful reminder of a test question you might have missed, and that has to do with the most important factor associated with heat of combustion is the number of carbons. And 8 is more than 5. All of these compounds below have 5 carbons, and this one up here has 8 carbons. So the most important factor is the number of carbons. And that's the only reason that 1 octene even makes its presence felt on this table, because the rest of the table is what we care about. I just want to make sure that you remember that most important thing is the number of carbons. Now we look at the degree of substitution, and this is going to require us to draw the structures of all of these compounds. So let's come over to ChemDraw, and let's draw some structures. All right, so we want 1 pentene, so let me just kind of spit out a bunch of 5 carbon groups and some 4 carbon groups. So 1 pentene means that I have a double bond at this position, the 1 position, and 3-methyl-1-butene means that the double bond is at the 1 position. Oops, missed. And there's a methyl group at the 1 position. Sorry, the 3 position. Again, still can't count today. So there's 3-methyl-1-butene, and there's my 1 pentene. We want Z2-pentene, so we're going to take this compound right here, and we're going to move it over. We'll go ahead and name it. And what I want to do now is just move that double bond over 1 position. So that's the E2 version of that one. Let's get the Z version of that one up there. For the Z, we just need to swing this one down. And now we have Z2-pentene. Let's check on our list here and get rid of the ones we've already drawn. We've got 2 left, 2-methyl-1-butene and 2-methyl-2-butene. So I'm going to grab this structure, and we'll use this as a template. I have a 2-methyl-1-butene, so let's go ahead and move that methyl group over 1 position. And that's the 2-methyl-1-butene, and now I need 2-methyl-2-butene, which is going to have the double bond at the 2 position right here. There we go. Okay. So now we have a little nomenclature practice. We took all of those questions, all of the compounds off the table, and we just drew all of them. Oops, going to move that one down, and now I can look at all of them. So the point of this question is to get you to look at the structures of these compounds and determine their relative order of stability based on your understanding of structure. And the first criteria was to first make sure everybody has the same number of carbons. And all of these compounds right here have 5 carbons. And if you're not certain of that, pause the video and go ahead and start counting carbons. And then come back and apologize to me for not trusting me that they all have 5 carbons, even though today has not been a good day for counting. All right, so the first thing we want to look at, the second most important criteria after you deal with the number of carbons. So criteria for stability. Number 1 is, now this is for stability, and so we really can't say the number of carbons is the most important criteria. That's the most important criteria for the heat of combustion. So remember that if you're going to burn things and you want to say which one is more stable, you have to make sure that they all have the same number of carbons. So we're not going to include number of carbons in our stability criteria because that's really just the number of carbons has to do with heat of combustion. And so we're going to actually set this up as substitution. Substitution. And then the second criteria, and it's tied with 2A and 2B, is something called, we're going to call this the steric effect, will be 2A. And then 2B is the electronic, and they're both called the effect. So I'm putting them in the order that I said them, but again, this note that these 2 criteria right here are tied is important, and we'll come back to that in just a second. Let's first deal with what we mean by substitution. The substitution does not refer to the substitution of any one carbon. Instead, it refers to the entire substitution of the double bond. Every single every single alkene double bond has 4 things coming off of it. Okay? And for this compound, 1-pentene, there are 4 things coming off of the double bond. So what I mean by that is let's first Focus on the double bond. This is the double bond that I care about, and it has 4 bonds coming off of it. In one pentene, 3 of those bonds are going to a hydrogen, and 1 of them is going to a carbon. So this is referred to as monosubstituted. We're going to use that same criteria now and look at E2-pentene. And on E2-pentene, there are 4 things coming off. We have 2 hydrogens right here. There's a hydrogen right there and a hydrogen right there. So in order to determine what kind of substitution it is, you ask yourself, of those 4 things, hydrogen, carbon, how many of them are carbons? And the answer is 2. So this is called disubstituted. I understand students have a tendency to refer to this as a secondary double bond, and this is a primary double bond. But it's not. It's referred to as monosubstituted and disubstituted. This is also monosubstituted right here. Monosubstituted. It's monosubstituted because off of the pi bond system, of the 4 potential locations, only 1 of them is not a hydrogen. This is disubstituted. I'm just going to copy and paste that. And hopefully you can pause the video at this point and just say out loud to yourself what the other 2 compounds down here are. Okay, hopefully you said that this one on the right-hand side was disubstituted, and this compound over here on the left-hand side is trisubstituted. Trisubstituted. All right, so here are my 5 compounds. I'm going to clean these up just, my 6th compound, clean them up just a tad, and we'll get rid of the hydrogens here just so we can kind of see everything without the clutter. And now that we have this criteria for stability tells me that I first want to divide them up based on the substitution categories. So these compounds over here are my monosubstituted compounds. These 3 are my disubstituted compounds, and this one all by itself is a trisubstituted. So I've broken these up now into 3 different categories. And based solely on substitution only, I can say that the more substituted it is, the more stable. I'm going to write that down so that you do as well. More subbed is equal to more stable. And therefore, this compound right here is the most stable. Okay? And this group, I'll just say this group is the least stable group right here. Least stable. And then this one here is in the middle. And that's just based on the most important criteria, and that is substitution. Now, to split hairs over these 2, about which of these 2 is the least stable, this is actually based on what we learned with alkanes, that with alkanes, if these were both alkanes, and we got rid of the double bond, then you would say, oh, well, this alkane is more substituted, and therefore it's slightly more stable, and that statement is still true. A more substituted alkane is more stable, just like a more substituted alkene is more stable. So because this alkyl portion is more substituted, then of these 2 right now, this compound is the least stable, and this one is not that much better, but it's the second least stable. Okay? And this is not a criteria that we're talking about today. This is simply a criteria associated with alkanes because they're only different on this alkyl portion right here. So least stable and most stable. Now, definitely the way that I'm going to ask this on an exam is you'll be the drop-down lists where you have to rank these compounds from 1 through 6, where 1 is the most stable and 6 is the least stable. This would be 1, this would be 5, and this would be 6. Now we have to figure out what 2, 3, and 4 are going to look like. So I'll prepare second most stable, and then we're going to have third, whoops, it doesn't like where I'm trying to draw on this. All right, I'm getting my labels all ready to slap them on these compounds. This would be the 3rd most stable, and this would be the 4th most stable. All right, so first place was definitely this compound because it is the most substituted. Substitution is the most important criteria. The other 2 criteria are referred to as sterics and electronics. So for these, let's go through each one and think about the steric effects. Steric refers to the ability of the groups on either side of the double bond to bump into each other. And for trans double bonds in general, the ability of these opposite sides to bump into each other is limited because they're on the opposite sides. So here we say the sterics are good, meaning that there's very little steric strain because the two groups coming off the double bond are on the opposite side. In this compound over here, the sterics are bad, and that's because the methyl group and the ethyl group are pinched by that double bond and get stuck on the same side. And the biggest issue occurs when this little alkyl group is swinging around, like it's, doing the 360, and it will bump into the hydrogens of this methyl group on the other side. And so that's where you see the steric effect. I can kind of animate that. That's never thought about using ChemDraw as an animation tool. But now let's put one of those hydrogens, and as this thing is doing loop-de-loops around the end of this methyl group, it's going to bump into that hydrogen from time to time, and that's the steric problem that we run into. Hopefully you can appreciate that all the loop-de-loops in the world are not going to put this ethyl group over anywhere near this methyl group's hydrogens at all. So sterics are bad right here. Sterics are good. Over here, what we end up with is actually sterics are good. And the reason for this, and they're not great, but they're good enough, is because both of the groups are coming off of the same carbon, then we don't worry about them bumping into each other. It's only when they're on opposite sides of the double bond that we start to see steric problems. So this is not a cis arrangement. The ethyl group and the methyl group are not cis relative to each other. They're coming off the same carbon, and the carbon's geometry of trigonal planar itself actually kind of addresses the problems associated with sterics. So we don't worry about the steric problems with the groups coming off the same carbon. We have to worry about the steric problems with groups coming off opposite sides of the double bond. So this one, the sterics are good. And this is where my my animation kind of breaks down. And the truth is that this methyl group itself would actually never swing this direction. It just kind of does this thing out here on the edge, and it never really bumps into this carbon or this carbon right here. So sterics are good, sterics are bad, sterics are good. I'm still trying to come up with second, third, and fourth. I need to compare these two characteristics simultaneously. So what I've done now is establish the steric criteria. Now let's look at the electronic criteria. In summary about the steric criteria is cis is bad, trans is good, and if both groups are coming off the same carbon, that's good as well. And so it's the cis ones that we're on the lookout for when we're worried about the steric effect. The electronic effect has to do with the cluster of electron density. Remember I said that alkyl groups in general tend to push electron density into the sp2 hybridized carbons. And so this is pushing in, and this one is pushing that way, and this is, wrong way. This electronic effect is absolutely related to the polarity example I gave you before. And what I tried to point out in the previous example is that it is the axis of the pi bond that matters the most when we kind of ask, what are these groups doing? So relative to the axis of the pi bond, you have one kid on one end of the bathtub that is basically pushing the water more or less to the left. And the kid on the other end of the bathtub is pushing the water to the right. This results in an unfavorable, unstable buildup of these pi electrons in the center of your bathtub. So when you have these groups that are pushing, they're working against each other, that actually produces a bad electronic effect. We refer to this as a negative electronic effect, but using these terms of good and bad, we're going to refer to this one as the electronic effect is bad. And it's bad because these two groups are working against each other. In the Z2 pentene, they're also working against each other along this axis that we really care about. We have one kid that's pushing the bathtub water more or less to the left, and the kid on the opposite end of the bathtub is pushing the water more or less to the right, and you end up with that unstable buildup of electron density kind of sandwiched in the middle of that pi bond. Those electrons want to spread out as much as possible, and if they are getting pushed, they prefer that you push them with agreement. So this has a bad electronic effect, that the electron density is being piled into the center of the bond, and that's unstable. With this compound right here, the 2-methyl-1-butene, notice how the electron density along this axis, now they are working against each other along the vertical, but we don't care about that axis. We look at left versus right. These two generally agree with each other. They're both pushing electron density more or less in the left, kind of in the left side. So you have a kid pushing up and over on the water, a kid pushing down and over on the water, and the water slides over here to the right hand, to the left-hand side. And that represents a good electronic effect, that these groups are pushing the electrons in agreement with each other. So the electronic effect is good. What we are trying to avoid is cross motion, where one of the groups is pushing the electron density into the pushing of the other group as well. Here they're in general agreement. Both of them are working these electrons to the left-hand side, and that's a stabilizing effect. So now I'm ready to go ahead and add in my second, third, and fourth most stable, just based on the fact that first I divided them up into the dye-substituted criteria. So I'm going to put that label out here on the side, and we'll get rid of this, and the mono-substituted right here, and the tri-substituted down here. I first divided them up into mono, tri, and di. The mono are the least stable, and then I split hairs based on the branching of the alkyl portion. The tri-substituted is the most stable, and there's only one, so it's all on its own as the most stable compound. And then these di-substituted compounds we have to split hairs over the steric effect and the electronic effect. And the way we read this is, this has a good and a bad, this has a bad and a bad, and this has a good and a good. So if both of the effects are good, then this is the second most stable. And both of the effects are bad, then that would be the fourth most stable, and good and bad leaves this one with the third most stable. And so there is kind of a complete answer that has to do with dividing these up by stability criteria. What I would encourage you to do is look at the examples in the textbook problems. They're going to have you do a very similar analysis, and you're going to go through and answer the question in the textbook to get more practice on this type of rationale. Let's go ahead and fill in all these answers now. How does the degree of substitution affect the stability of the alkenes? More substituted equals more stable. How do sterics affect the stability of the alkenes? They are the lesser, it's like least important criteria. And it's based on the cis versus trans of the groups across the double bond. And cis is bad, trans is better. And then finally, the electronic effect. This is also the least important criteria. And you want to make sure that you include a note that these two criteria, steric effects and electronic effects, are tied at around a rock bottom criteria, and it's based on the push/pull of electron density across the pi bond, parallel to the pi bond. And a good electronic effect occurs when groups are pushing or pulling together in the same direction. The electrons are not confused by mixed signals from the groups hanging off of them. All right, and then we have the example and all the criteria of these. Now let's look at the data to make sure that it actually matches our criteria. The one with the highest heat of combustion would be the least stable. And so, again, excluding the octene because it has the wrong number of carbons, but the 1-pentene is the highest heat of combustion, so it is the least stable. Then the 3-methyl-1-butene is the second least stable. So that's this one. And so least stable, second least stable. The lowest heat of combustion is this 2-methyl-2-butene. That's the 2-methyl-2-butene, most stable because it's tri-substituted. And then we spent a while splitting hairs over these three compounds right here. The Z2-pentene was the one that had steric and electronic problems. So of the three, It was the least stable, highest heat of combustion. The 2-methyl-1-butene had the lowest steric problem because both groups were coming off the same carbon, and the smallest electronic problem because the groups were pushing together relative to the plane of the pi bond itself. So this data should match. These data should match what we're seeing here with our description. What about cycloalkenes? Well, we typically don't designate cycloalkenes as E or Z. And the reason for that is, let's just clean all of this off. When you have a cycloalkene, let's consider the smallest possible one, you really can't have anything besides a cis-like arrangement, which would be the Z arrangement right here. If you imagine, let's say that you try to put a trans double bond inside of a cycloalkene. So remember that these carbons right here are sp2 hybridized, so they want a bond angle that is 120 degrees. And so let's put a hydrogen right here and a hydrogen right there. And now how am I going to attach those two ends of the carbon together? Well, I'm going to have to build this thing for a bit. I come out here, build my bond. I can't have a straight line, so I can't build this direction because there's a hydrogen there. So I'll come out here and then over, and then I'll kind of cheat a little bit, and eventually I'll get to that carbon right there. And so yeah, now I have a trans double bond inside of the system. Let's see what Control Z does. It does not care for that compound very much. And the name for this compound would be cycloundecene. So this is 11 carbons. So what I'm suggesting here is that I need about 11 carbons, and even then, this is a mess. This hydrogen's bond angle is supposed to be over here, but it can't because it would run into that carbon. So actually, the data would suggest that you need about 12 carbons to be able to build a normal alkene with a trans-like bond in there before it starts to become really problematic. They have actually in the laboratory been able to synthesize a 7-carbon trans double bond, but only at really low temperatures, because as soon as the temperature goes up, then that double bond pops. The thing kind of unfolds itself and then reseals back together again as a 7-membered ring system. This is an 8-membered ring system. I believe that they can put a trans double bond in one of these at room temperature, but it looks really goofy. I think it looks something like this. It looks kind of like this. This is 1, 2, 3, 4, 5, 6, 7. Did I do that right? Yeah, that should be 8. Yeah, cyclooctane. And they have been able to build a cyclooctene like this. But the problem is with cyclooctene is that there is this hydrogen right here, and it's planar, and it's just sticking into everything. And so really hard to build one of these. They did manage to do it. It was kind of a big deal to the chemical world because you built something you weren't supposed to, but it was highly unstable. So normally it's about 12 carbons is where you start to see these things showing up. So what that means is nobody bothers to really build to tell you that your double bond is E. So if we draw the label for this one, they're like, oh, of course it's a cyclopropene. And you're like, well, what direction is my double bond? Is it E or is it Z? And they're like, get out. It's definitely going to be a Z, and there's really not any options. In fact, one of the funnier things, and I wonder if ChemDraw still has this built into the software, if I try to say let's say E cyclopropene, you can actually ask ChemDraw to build you this structure, and their response is a very, last time it was a very polite no. So you can convert the name to a structure. Whoops. This one is, so I'm going to do that. Yeah. And you notice what they said right here. They're like, stereochemical term discarded, E. In other words, take your E and go away. That's what the ChemDraw is telling me right now. That we're going to go ahead and build this in the Z configuration, and your E is meaningless to us. In fact, they do it all the way up. Let's see if they'll do it with cycloheptene. Nobody is excited about this except for me at this point. Nope, still got rid of it. Still did not like that stereochemical term and just spit out the 7-carbon ring at you. Obviously, they're not looking at the literature to find those rare exceptions where people have actually been able to build that. Cyclooctene. Oh, and finally, it did what I said. So the robots have not rebelled against me. So back to the question now. Small cycloalkenes are typically not designated as E or Z. Why? And the answer is because they are all Z. Okay? And then we want to draw E-cyclohexene and explain why is it extremely unstable. Well, ChemDraw wouldn't let me do it. So I'm going to try to put, also I got to start with my trans double bond right here. And I'm going to have to connect these two ends together. So I've already spent 4 of my carbons right here. I only have 2 carbons left. So there's 1 and there's 2. And now we tie everything together. And let's see. When I clean this right there. Yeah, so now you ask, well, why is this extremely unstable? Let's copy that back over. That this is blasphemy to even put this on a chemical homework assignment because that compound's going to have all kinds of problems. Why is it extremely unstable? And you're like bond angle. And sterics. And flammability, I guess. Yeah, this is a mess. There you get this. What is this, like a 12-degree bond angle right there? There's no way that a compound's going to put that in there. The 2 diastereomers of cyclooctene have heat of combustion value that differ by 39 kilojoules per mole. To kind of appreciate how impressive that is, the difference between all of these different alkenes that we looked at was 349 was on the high end, and 3328, that's a difference of just about 21 kilojoules per mole. So on this list, my least stable version of a 5-carbon alkene was 21 kilojoules per mole less stable than the most stable version of that I saw. And when we look at cyclooctene, they differ by 39 kilojoules per mole. That's a large difference. We can let ChemDraw do this for us, but I've already drawn this a couple times. Here's cyclooctene right there in the Z configuration. And then we're going to draw cyclooctene in the E configuration. We'll build this, and we'll put that right there, and I'll make sure to put my double bond in a trans position. And so these are the 2 that the question is referring to. Why are they so different in terms of energy? Well, it's because this one has steric problems. That hydrogen coming off of this carbon right here either has to bend at an inhuman angle. That's just cruel to do to a hydrogen right there. Or it's got to run right into that carbon. There's just no way to do this. No good way to do this. It does manage to do it. And so we're going to take those 2 structures and use them as part of our explanation. And we can just say that this E-cyclooctene has bond angle and steric issues. Kind of in the same way that Joker has issues. Like, they're pretty extreme issues at that point. Okay. What is the homework asking you to do? Oh, you get to name some of these. This gets to the rules of nomenclature that we want to use. One of the tricks that you're going to like when you go to name these compounds is this one right here. When you have a 2-carbon substituent, this actually has a common name. It's called a vinyl group. And the vinyl group right there kind of helps you out a little bit. You can just call this a vinyl. And this one is a trivinyl. And so that will help you name these things a little bit more easily. But we'll stop there. I'll let you guys work on the homework. And then tomorrow we'll come back and look at some more complicated examples of E and Z alkene nomenclature.